The next exercise is going to be a little different in its format. It's going to ask you to retrieve some of the information that is in the lecture, but by yourself, by doing things in an active manner. So I really encourage you to try to do it first on your own, then come back to this video so that I can try to run you through. But as soon as we address one of the problems that you bump into, pause the video, try again to get the next step done on your own, then come back to the video and so on and so forth. This is the best way to make usage of this particular video, okay, in order to maximize your learning. So let's take a look at what we are dealing with here. We are dealing with a very simple program that we're going to write together. So we're not trying to solve so much a problem, we're trying to actually write code that illustrate how the compiler and the language underneath are interpreting what we what we type. Okay, so we are pretty much learning the properties of the language by tinkering, which is a very, very good skill to learn when you are going to program in your career. So what we have here is we have a little program where we want to declare an array of 3 integers, okay, that contains 1 to 3, and then we want to display the memory address at which are located each of the elements of the array, and then display the memory address corresponding to my array, okay? And the question here is, what does that tell us about the way that my array is interpreted by the compiler? So go ahead, give it a shot, and then I'm going to expect you to come back and we are going to work on that together. So let's write the code. The code is going to be very simple, okay? Int my array, and I'm going to say, you know what, let's use pound defined constants. So I'm going to say I have a constant my array size, and I'm going to initialize that to a bunch of values. So the bunch of values is going to be 1, 2, 3. Okay. So I'm going to say pound define here, precompiler directive. I want to define a symbolic constant called my array size. So everywhere the compiler is going to see my array size spelled like that, it's going to replace it by the value 3. Okay. So it's kind of like a cut and paste with macros. All right, so I have this taken care of, and just for why not effect, we are going to replace that also by my array init block. Okay, and I'm going to say, just to show you that you can do much more than just like numerical constant, with the symbolic constant. You can really say every time you see return my array init, you replace it by this. Okay. So it allows you to have like things that are really convenient, like for example here, those 2 pound define directive that tell me the size of the array and what's in it. And then throughout the code, I don't have to worry every time I'm going to update this one, like the size go to 4, for example. I'm going to also be able to update the initialization right the line below so that I don't forget. Okay. All right. So we have this taken care of. Next thing we need to do is, well, first we should compile always. Always compile, get rid of typos and stuff like that. And then if I run it, of course, it doesn't do much yet, but there we go. So now what they are telling us to do is they're telling us to display some sort of header. This is a step 1 of the exercise. Okay, so I'm just going to display step 1 here, but you can find in the Word document a little bit more lengthy narrative there if you want. I'm going to display step 1, and then I want to display for every element of my array, I want to display the address of that element of the array. So I want to loop for int I equals 0, counter control loop that's going to iterate over every element of the array. I lesser than my array size. I have the constant, let's use it, right? I plus plus. And every time what I want to do a printf. A printf, I'm going to do a tabulation so that everything that is about step 1 of that display on the screen is going to be indented to the right under the header step 1. Okay, so it's just visual. Okay, and I'm going to say I want to display the address of my array index, and this is going to be index %d because the index is going to be given to me by the variable I. Okay, and I want to display that is equal to, and the actual value equal %p. So to display a memory address, %p, right? And the memory address is going to be the address of my array index I. Okay, so just a little program that's going to pretty much show on the screen the memory layout of all the variables that I'm using. Okay, once I'm done with that, the next step that is asked of me is to display one more information, printf, and I want to display still indented, and I want to display what my array is equal to as a memory address. And I'm going to therefore put here my array. There we go. Save this. So let's give it a compilation run. Let's run it. What do we obtain? So step one, okay, sure. My array index 0 is at this memory address. Hexadecimal number start with 0x to let me know that this is going to be hexadecimal. You can see that I'm using like the letters A, B here, E and F, so this is definitely hexadecimal literal that we're talking about here. This one start at address blah 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 00. The second element of my array is at address blah 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 blah, same exact address 04 as the two last digit. The next one at address blah 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 08, and the next one at address 0c. So what's the deal between 0, 04, 08, and 0c? Well, between 0 and 4 there are 4. Okay, that's not really like college material, but between 4 and 8, again 4. Between 8 and C, C is an hexadecimal letter, right? So there is also 4. C corresponds to actually 12 in hexadecimal, okay? So what we have here is we have an idea of the memory layout of my array, okay? And I'm going to grab a pen real quick, and we're going to jump here to the whiteboard so that I can illustrate this. So here's my array here, somewhere, my array, okay? And what we are saying is that we have 4 elements in that array. Sorry about the lines not being really horizontal there. This one start at address blah 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 0, blah 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 4, blah 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 8, blah 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 C. Okay? So the distance between the size of each element of my array is pretty much 4 bytes. Okay? So this is very useful for us to be able to go between the code, like for example, I'm declaring this, okay, my array size, etc. The memory diagram that includes memory address is to see exactly where everything is ending up, and also as the code itself, as it runs, display information about itself, which is called sometimes instrumenting a piece of code, and let us know where everything is located in memory. So this is kind of a way for us to kind of connect all the dots together, and this is very useful. So whether you use a debugger or you use a simple printf statement, instrumenting your code, looking at your code as it executes and looking at the memory address where things are located is a great way to learn more about pointer manipulation. Okay, because you're starting getting comfortable with memory addresses, the offset between elements in an array, and things of that nature. And then the last bit of information that is being displayed here is my array equals the same memory address, 00 at the end. So this is the point of this whole little exercise, and the first question of this exercise. What does this mean? That means what I already mentioned in the lecture, which is the address of the first element of an array is actually what the name of the array refers to. And you can tell it here, like when I do a %p of my array, this is what I get, the address of the first element inside that array, okay? So it's repeating what we covered already in the lecture, but it's very easy to miss it or misunderstand it, when you're just being told. What I hope is that by having you implement a piece of code here and actually tinker with the code, display the memory address of different things, etc., then you're not only retrieving this information that was in the lecture, but you are seeing here how I would go about, for example, figuring out things about a programming language if I was new to that programming language, and I would just have access to a compiler to try little programs and do things like that. Okay, if I want to verify or discover the fact that the name of the array represents the address of the first element, this is a very easy way to do it. Doing things that way, this is what I refer to as learning by tinkering a programming language. It's, again, very useful. You're going to use that a lot in your career. So that's it for the first question here. Let's move on to the second question. The second question is about pointer arithmetic and subtraction. The next one is going to be about pointer arithmetic and addition. So we are trying to subtract and add to pointers, and we want to make sure that you understand what happens when you subtract and add value, what is the meaning of those operations, what is their semantic. So we are going to add a little bit of stuff to our code, okay? The instruction tell us that we would like to display the address of the first element. Actually, let me go back to the instruction because I think I'm going in a loop here. No, we want to display again the address of the first element, address of the second element. So we have done that already with the loop, but now we're going to do it, like one at a time with the code that is given to us here. And then we want to do the difference, the subtraction of one memory address to another memory address. So there are two things that you can do with pointers and subtractions, right? The first thing you can do is add an integer value to a pointer. Okay, so adding or subtracting an integer value to a pointer, we're going to cover that in the next step. But the second thing that you can do when you're doing subtraction with a pointer is do the subtraction between two pointers. And this is what this part of the question is more focused on. So we want to make the difference between the address at which this element is located and the address at which this element is located. Okay, so let's jump in the code and let's do exactly that. So I'm going to add a little bit of code here. I'm going to keep this. I'm going to put a printf step 2. Okay, and there's going to be a printf step 3 later on. Okay, I'll leave it for now. So printf step 2, we are going to printf the first address. So first address is %p. Let's do a little tabulation here. And actually, I should put everything under a tabulation as well here. So the first address is %p, and this is going to be the address. Is going to be the address of my array index 0. And then I'm going to cut and paste this because it's going to be very similar. And I'm going to say the second address I want to display. Second address is my array address of my array index 1. So the address of the first element of my array, the address of the second element of my array. And then I want to display the difference between the two addresses. And I'm going to express that as a size t, okay? So the difference between, like size t is this wonderful type that corresponds to a long unsigned int, actually. But this is this wonderful type that allows us to keep track of indexes in arrays, to keep track of memory differences between differences between two memory addresses, stuff of that nature. Every time you have an index or something like that, use a size t and display it using the %zu format specifier. So here I have this, and I'm going to say address of my array index 1 minus, and let me spell my array here, minus the address of my array index 0. And not the $sign, but the ampersand sign would be better. All right, let's save this. Let's take a look at what we have here when we compile. No compilation error, perfect. Let's run it. So first address is, so first thing to notice, I reran my code. The memory addresses are different. Okay, yep, that happened. This is perfectly fine. So they are different, but they still follow the same logic. 0, 4, 8, C. Okay, so the number here could be different, but what's important is that there's 4 bytes of difference in every between every element of the array, because they are int, and int are encoded in this particular virtual machine with 4 bytes. Okay, the address of the first element of the array is still what is used to represent the array. Okay, so that all of that is constant, but the memory address themselves change. So here's my first address again. Here's my second address again. The difference should be 4. The difference is 1. Why? So if you don't have the answer right now, I suggest go back and take a look at the lecture real quick. Okay, play ×2 if you want, but you missed something important. Okay, so go back to the lecture and make sure you didn't miss anything important and anything else that is also important. Okay, and then I'm going to kind of like give you the solution here in a second. So the difference that we expect would be 4 if we expected a difference expressed in bytes. Okay, the difference that we get is 1. So the difference between those two memory addresses is definitely 4. Okay, this is the first one, this is the second one. If I do the difference of those two hexadecimal numbers, I'm going to get the value 4. But here I get a 1. Why? Because I'm talking about pointers on int. I'm talking about memory address of int element. So it's not good enough in C to say I have a memory address. Okay, if you just have a memory address, we call that a void pointer, a memory address on nothing, because we cannot really use that memory address to do anything at that memory address. Okay, to be able to act upon a location that is located as a specific memory address in memory, you need to not only know the location, the memory address, but you need to know also the data type. You know, the data type is of what is being referred to. The data type is going to tell you how much space in memory you need to read or write at that address, starting at that address, and it's going to tell you how to encode the bits. Like it's different if you encode an int, if you encode a character, if you encode a double or something like that, right? So this information about that is very important, and you can see here that when you do the difference between two memory addresses, this being memory address of int element, the difference is going to be expressed in a unit that is the size of an int element. The size of an int element is 4 bytes on this system. The difference is 4 bytes between the address, so the answer is the difference is 1 size of an int element. Okay, very important. Okay, you have to understand all of those little things to be able to use pointer arithmetics. Yes, it's very detail oriented, but so is programming. So make sure that you ask questions on the forum or Piazza, depending on what we use the semester, if any of this is not making sense, or come even to office hours. Okay, and we'll go over this with you. Make sure that you are comfortable by the time we are done going over it with you. All right, so that's pretty much what we are trying to do here, okay? So this is the kind of point that this particular question was trying to make you reflect upon. And then what we do here is we create another pointer named P. We put the address of the element myArray index 2, and then we display those values on the screen, P-1, P-2, P-3. So we are talking about the other aspect of the subtraction with pointers, okay? Subtracting one pointer to another, this is what we did here, computing the difference between two memory addresses. And now we're talking about subtracting an int value, okay, a positive int value like 1, 2, or 3. So let's do this. Let's add a pointer. Let's make it point to my array index 2, okay? And then we are going to display printf p. So let's start by displaying p, okay? P is, and we're going to display %p, there we go, and this is a value of my pointer, okay? So my pointer should have the address of the element at index 2, which is the third element inside my array, okay? And then so I added this. This was not required by the requirement, but it's going to make things a little clearer. And then I want to display P-1, and then it's going to be P-2, and then it's going to be P-3. That's what the requirement asks me to display. Okay, I just threw in the value of p for free. All right, let's save. So the programs are easy to write. What is important is that you run them, you see what they display, and you understand every single thing that they display. So the pointer p is set to point to element at index 2, in my array. There we are. P is equal address of my array index 2. So my array index 2, this is a memory address. Again, the memory address changes from execution to execution, but the logic of their relation with one another didn't change at all. So this is the address of element at index 2, which is inside of P. So far so good, we can make sense of that. If I subtract 1 to P, I should get 0x7ff blah 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 8857. No, same thing. When you subtract an int, you are not subtracting 1 byte to the address. Okay? What you are subtracting from the address is 1 times the size of the element that are being referred by those address. Those memory address, because we are talking about an array of int, are pointers on int. They are memory address of int element. So every time you subtract 1 to the memory address, you subtract actually 4 bytes. So here we are. We go from 58 to 54, then 54 to 50, 50 to 4C. Okay? So this gives me actually the memory addresses of some of the elements that I had before, right? Like this one, this one, this one. Okay? All right. What else? What else do we have here? Well, that's pretty much what was asked of us in this requirement. So we can move on to the next step, I'm guessing. The last step, are these the same thing that subtracting 1 from the hexadecimal value? I already covered that. Okay, no, it's not the same thing. Why so? Because we subtract by unit of the size of an int element. Last part of this exercise, we are going to talk about addition now when we add numbers to our pointers. So what we are going to do is we are going to do something, we are going to re-implement something that we used already in the lecture, but again we are going to kind of look at what the code does in detail, etc. So try to reinforce the data, the pure data that was sent to you through the lecture by recovering it in a hands-on manner, learning by tinkering again. So what we want to do for step 3, we want to use a pointer to iterate over the element of my array. So I'm going to use a loop, okay? And inside of this loop, I am going to do a printf, and I'm going to say inside the printf, so indentation, because it's all belong under step 3, which I already displayed the header for here. I'm going to say this is iteration number %d. So I'm going to have an index, okay, an index I. So let's start with that. For int I equal 0, you know what? I'm going to declare I here. Int I, there we go. You're going to see why in a second. For int I equals 0, I lesser than, so it's going to be the same than before. My array, I could have done a cut and paste, and then I plus plus. So I'm going to iterate over all the indexes of my array. I'm going to say, okay, this is iteration number I, and then for each iteration, I'm going to put a tabulation here, and I'm going to say my pointer p, which I'm going to declare in a second, is %p, okay? And then I'm going to say what is pointed by p is, and this is going to be a %p. So %p because it's a pointer, it's a memory address, %d because what I point to with that pointer is going to be actually one of the elements of the array. So I need to add some stuff here, I need to add p, I need to add star p, and I need to define these. So I'm going to say int star p, and just because I want to demonstrate good habits, I'm going to initialize my pointer to no. Every pointer that you don't have a value to initialize with, that makes sense, should be initialized to no so that you can detect bug more easily. And p is going to be set initially to, there should not be a comma here, there should be a semicolon, but now I'm going to add a comma, and I'm going to say I want to assign 0 to I, and I want to assign to p the value my array. So the address of the first element of the array, right? And at the end of every iteration, I'm going to increment I, and I want to also increment p, so p plus plus. Okay, all right, let me make this a little bigger because it looks like, you know, I typed p plus minus plus, but no, I typed just p plus plus. So with this, what I have is I have I set to 0 and p set to the address of the first element before I start my loop. Then as long as I is lesser than my array size, I'm going to display the value of I, the value of p, what p is referring to. So in the first iteration, the value of p will be the address of the first element. Star p will be the value of the first element. And then I'm going to increment I. I'm going to increment p. So incrementing p plus plus means p equal p plus 1. So I'm adding 1 to p, just like when you subtract 1 to p, you don't just add 1 byte to the memory address. What you do is you add 1 times the size of the elements being pointed to. In this case, we're pointing to int elements, so I'm adding the size of an int, which is 4 bytes, okay? So I'm incrementing p by 4 bytes here, and then I'm displaying what is referenced by p again, and I keep going like that, iteration after iteration, until I have iterated over every element of my array. Well, let's see how that works. Let me save the file. Let's compile. So I forgot something, redefinition of p. Ah, yes. I have already a p here, so I don't need to redeclare it, but I can reinitialize it to know because I need a brand new value in it. There we go. And then a dot out. So now it's the time for the right side window to be a little bigger. Step 3, let's just look at step 3 because everything else here we already covered, right? And it's going to be different memory address but same logic. Step 3 is interesting because step 3 tells us iteration 0, p is 0x7fff blah 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 430. Well, that's the address of the first element. That's what we wanted. We wanted p to point to the first element of the array. Star p is 1, yes, because my array contains 1, 2, 3, 4, right? If I go back here, this is still visible here, right? So I have the value 1 in the first element, then 2, then 3, then 4. So you can see that I'm iterating here with the pointer p. I'm pointing to the first element during the first iteration, to the second element during the second iteration, third element during the third iteration, fourth element during the fourth iteration. And then the value of p, this is the address of the first element. This should be the address of the second element, bingo. This should be the address of the third element, bingo. This should be the address of the fourth element, bingo, as well. Okay? So we did an iteration like that in the lecture. We use the pointer. It's written a little bit differently here. I mean, I've been using the comma operator here, which is a minor detail, you know, for the for syntax. So we did pretty much the same thing here, written maybe a little differently. I think I was using a while loop in the lecture. But the bottom line is that you can see that if you instrument your code, if you display actually additional information as it runs, or if you run this with a debugger and inspect the content of memory as you step through, you know, step by step, you are going to gain a much better understanding of what's going on. Okay, you're going to be actually able to see practically what is happening in memory, and this is generally it makes things a lot easier for the learner. Okay, there you go. That's pretty much what we had to do, and the last step is modify the code. So now we have an array of double instead of an array of int. Not a problem at all. So this is going to show us, you know, that those +1, -1, and stuff like that are actually different when we have an array of int instead of an array of double. So I'm going to say my size is still 4. I'm not going to rewrite code. I'm going to modify the code that I have. And I'm going to say that the values are double values. Okay, instead of an int my array, I'm going to say my array is an array of double. Okay. Okay, so this is all right. Then I'm going to display my array index I, and I'm going to display the address of each element. This doesn't need to be modified. Display the address my array doesn't need to be modified. Display the address of the first arrays and their difference doesn't need to be modified. Whether it's an array of int or an array of double, the code is going to be the same. Here we need to modify things. So p is a pointer on not int anymore, but double. Okay, and it has the address of the element at index 2, and then I can display p minus 1, p minus 2, p minus 3, okay, no problem there. And then step 3, let's see, int I, p equal null, p equal my array, all of this is good. P++, again, the fact that p points on an int or p points on a double, when I do p++, I increment by 1, but it's going to be 1 times the size of an int or 1 times the size of a double, depending on how p has been declared. So this is going to be handled automatically. And then iteration, p%d, %p, and here instead of %d, I need a %lf because what I'm pointing to now is not an int, but it's a double. Okay. And then let's see if we were able to get away with doing as few modifications as possible. Well, it looks like it's working, but let's take a look in detail. Okay. So what do we have here? We have the address of the first element is 0x7ff blah 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 90. The address of the second element is 98. So the difference between the two is 8 bytes. Why 8 bytes? Because while an int is stored on 4 bytes in this particular virtual machine, a double is going to be stored on 8 bytes. Okay? So instead of going 4 by 4, we go 8 by 8. So 90, 98, A0, A8. If you make the difference in hexadecimal, every time we're incrementing by 8. The address of the first element is still what we use the name of the array for. When we do the address, the difference between two addresses of two consecutive elements in the array, the answer is still 1, thus showing that, yes, it's one unit, 1 times the size of the element that you have in that array. And then if I do p, well, this is the address of p once I set it to the address of the element at index 2, and then here's p minus 1, here's p minus 2, and then p minus 3, just like before, ends up before the end, before the start of my array, okay, because I was at index 2 and I did minus 1, minus 2, and minus 3 here. It's before the element that is not an element of my array. It would be the address of the double element that is before the start of my array. And then iteration 0 here, this is the first address of the first element, perfect. Then we follow the address of all the elements and we display the value 1, 2, 3, 4, represented as floating point number. Okay? So we were able to pretty much do exactly the same thing, and it's really important that you compare and contrast what happened with an array of int and an array of double, both at the code level, because we didn't have to modify much, okay, and in the logic of what is being displayed here, okay. Once you do that, you should have a better understanding, a more solid understanding of what's going on, or you should have a bunch of questions that you want to ask, okay. So either way, it's good for the learning. If you have a bunch of questions, don't let them, remain unanswered. Come to office hour, post on Piazza, post on forum, whatever we're using this semester, and the TAs and myself will help you get comfortable with this material. All right, as usual, thank you for your attention, and I'll see you in the next video.